Do you guys have a question so far?
None, sir.
All right, how about the others? Miss Hanimi, Charlotte, Mr. Yalin, Mr. Reister,
None, sir.
None, sir.
Mr. Gulaida,
Answer.
None, sir.
Mr. Daman, Mr. Zambrano, Miss Alaika,
None, sir.
None, sir.
and then Mr. Eda.
None, sir.
Seryoso guys, naintindihan nyo? Mamaya, puro kayo none. So if there's a part that you guys didn't understand, so please let me know. Okay, I'm very willing to help. Okay, so you can even message me anytime just to help you. Okay, so sir, I didn't understand the slide 20, so slide 20 to slide 25. It's quite confusing, blah blah blah. Okay, so you can message me so we can have a short meeting on that part. Okay. All right. So sabi niyo you guys don't have a question anymore then. Okay, so let's continue. So this is where we've stopped. Okay, so as you can see, we now have 4 diodes. Okay, and then still we have 1 voltage output. Okay, in the middle. All right, so moving on. 4 diode bridge rectifier. So when the positive input cycle progresses through the period t is equal to 0 to t halves, the polarity of the input AC signal across the diode and the output from the diode are as represented below. So if we have a positive cycle, okay, positive, positive, okay. So if you're going to take a look on this one, the other one will become a reverse bias, and then the other one will become a forward bias. So positive to positive, negative to negative, and then the other one is positive to negative. So this one will become up, since this one is in a reverse bias. All right, so of course our current now will pass through here. Okay, from here going to our V sub O. Why? Because our current won't be able to pass through this diode, since this one will become a reverse bias. Okay, so we have a positive here, and then it will lead us to a negative, which is now will become a reverse bias. So our our current will pass through V sub O, going down to this diode. All right, so still positive to positive and then negative to negative. So this one will become on, or a forward bias, and then going past through here and then going back to our ground or to our negative. So if you're going to simplify this one, from here to here to here to here to here to here up to the negative. Okay, so this is our positive cycle. Okay, so here D2 and D3 will conduct, and then a D1 and D4 will be in remain of reverse bias. Okay. So here's the complete flow of our positive half cycle. Okay, so here we can see that due to the special arrangement of the diode network in the bridge, so when D2 and D3 conduct, the opposite D1 and D4 will remain reverse bias and in switch off state. So net output DC generated from this rectification process through D2 and D3 are ideal diodes. Okay, so we're now considering that our diodes are ideal diodes. Okay, so if it's forward bias and completely closed switch, if it's a reverse bias and it's completely an open circuit. Okay, so since we have imagined the diodes to be ideal, the output is equal, of course, V sub O is equal to V sub I. Okay, so whatever is the value of our V sub I will be the same as our V sub O, since we are not considering the voltage threshold of our diodes. Okay, so here's the complete flow of our positive half cycle. And then likewise, of course, for the negative, if we have negative here and then positive here, so in the negative part, so it will pass through D1 and D4. Why? Since if you're going to take a look at this one, so this one should be negative to negative and then positive to positive. So this will make this one a forward bias. Okay, and then the other one is negative to positive. So this one now will become a reverse bias. So from here, it will pass through here. And then, of course, it will not pass through this diode since this one is positive. So negative to positive is a reverse bias. So this will become an open circuit. So now it doesn't have a choice but to travel through our V sub O. Okay. And then going through here and then here. So negative to negative and then positive to positive is a forward bias until it reaches the ground or the negative. So the flow of our negative is like this. So from D1 to V sub O, D1 to V sub O to V sub 4, and then going back to our ground. Right? So either of those two actually, as long as you have the correct polarity of your V sub I and then the diodes. All right. So for our negative half cycle, okay, so the positive half cycle, okay, so from 0 to t divided by 2 will become, of course, completely 0. And then for our negative, we'll now have a current, okay, or we'll have a voltage. All right. So thus, our positive will conduct, and then our negative will also conduct. So you can write this one as like this. Okay, so if we have these two, okay, two shapes, okay, it's like two mountains. So this one is completely full wave rectification. Okay, so unlike the half wave, where is that? Okay, there you go. Unlike the half wave, we have a slat or a vacant slat for this one. So a mountain, vacant, and then a mountain, and then vacant again. But for the full wave rectification, okay, so it's either on the positive cycle or the negative cycle. So in here we have positive, okay, one here and then another one here, which is representing a full wave rectification. And then before, as you can see, we have a VDC of 0.318, but in here you're going to use 2 divided by pi. So as I said a while ago, the number above the numerator, which is a 1 or 2, is the diode that our current or our voltage input passes through. So in half-wave rectifier, we only pass one diode, so 1 over pi. But in here, it passes now 2 diodes, so 2 over pi. So if you're going to compute that one, you'll get 0.636. But then again, in calculating the VDC, you don't need to use the 2 over pi, okay, the complete value. Instead, just use this one, 6.36 or 0.636, I'm sorry. Okay, so for half wave, 0.318. For the full wave, 0.636. Okay, right, so considering the VD of the diode, so now we're considering the diode as a silicon. Okay, so we now have to deduct the voltage threshold of the diode. So as you can see right here, as it passes through our first diode, it will now deduct or it will now consume 0.7 volts. Okay, going through our voltage output, and then as it passes through again our second diode, it will again deduct, okay, 0.7 volts. So we have this kind of setup. Let's say everything is silicon, then we could just say Vm minus 2 Vt. That is if those two diodes are the same. But if this one is germanium and then the other one is silicon, then you have to get the voltage threshold separately. So negative 0.7 and then negative 0.3. But since they are the same, then you can just say negative 2 times voltage threshold, which is 0.7. Okay, so everything is the same. Okay, everything is the same. So if it's positive, it will pass through D1 and then D3. And then if it's negative, it will pass through D2 and then, am I correct? D2. Oh, no, if it's positive, it will pass through D2 and D3. If it's negative, it will pass through D1 and D4. Okay, it's just that in here, you now have to deduct the voltage threshold, which is depending on, of course, the diode that is being used on this circuit. So on this circuit, we've used silicon as a diode. Okay, so using silicon diode in full wave rectifier, so as depicted in the above figure, which is this one, if instead of ideal diode, a silicon diode is used, applying Kirchhoff's voltage law over the conduction line would give us the following result. So initially we have the V sub I, of course, and then minus the first voltage threshold, minus the V sub O, minus another voltage threshold. So that's where we will get this equation. V sub I minus V sub T minus V sub O minus V sub T is equal to 0. So from here, we can combine or add those to the same variables, Vt. So from here, we could say that V sub O is equal to V sub I minus 2 Vt. Okay, so just simplify this one, and then, put the V sub O on the left side, and then the V sub I, and then 2 times V sub T on the other side. Okay, so same with this one, Vm minus 2 Vt to get the V sub O. So therefore, the output voltage peak V sub O will be V sub O max, or V max or V sub O max is the same, okay? So V sub M minus 2 Vt. Okay, so Vm is actually already our peak voltage here. But of course, you have to deduct the voltage threshold. So we just use another terminology wherein V sub O max or VO max is the process, okay, voltage wherein you already deducted everything, okay, specifically the voltage threshold. So V sub N minus 2 V sub or 2 Vt. All right, so as usual, your voltage input should be greater than twice of the voltage threshold, because if no, then no, you won't be able to process, or you won't be able to conduct current on that full wave rectification. So the same idea with the half wave rectifier. So V sub I should be greater than V sub T. But in here, since it passes through the 2 diodes, so your V sub I should be greater than those 2 diodes. So basically, you should have 1.5 volts and above, okay, for silicon. But for germanium, say 2 germanium, you should have 0.7 volts and above. Okay, so in a situation where V sub I is greater than twice of the voltage threshold, so we can use our earlier equation to get the average value with a reasonably high degree of precision. So again, in getting the VDC, so 0.636 times V sub N minus 2 Vt. Okay, so in half wave, you're going to use 0.318, but in full wave, you're going to use 0.636. So those are the things that you need to consider. And then V sub M minus 2 Vt, right? And then the other thing that you need to compute on the rectifiers are the PIV or the PRV. So those two are just the same. So we have the peak inverse voltage for the PIV, and then peak reverse voltage for the PRV. Okay. So basically those two are just the same, inverse or reverse. Okay. So it is basically a reverse bias voltage range of the diode that must not be exceeded. So otherwise, the diode may break down by transiting into a region called a Zener avalanche region. Okay, so we will discuss this one soon, maybe next meeting. All right. So PIV rating should be greater or equal to the V sub M, okay, or the maximum voltage. Well, initially they are equal, okay, depending on the polarity of the diode. Anyway, so we have this graph here, okay. So if it's an open circuit, so it is the maximum or the V peak voltage, okay, when it comes to reverse bias. So in getting the PIV, so it is now the value, or whatever is the value of this open circuit, then that is now our PIV, okay. Or to make it simple, whatever is the V peak of the forward bias, just put negative on that one, then that is already our reverse voltage, okay. So later on, I'll discuss more on PIV. So for a full bridge rectifier, also, the PIV rating calculation is the same as half wave rectifier. So that is PIV that should be greater than or equal to V sub M, since V sub M is the total voltage that's applied to the connected load as depicted in the following figure. Okay, so whatever is the voltage that passes through V sub O is our V sub N. And then whatever is our positive V sub N will be our negative, or will be our PIV, or peak inverse voltage. Okay, So this is our positive value, and then the peak inverse voltage is the negative value, okay, or the negative VM. Right? So let's have another example. So problem number 3, which is a full bridge rectifier network. So determine the output waveform for the following diode network and also calculate the output DC level and the safe VIB for each diode in the network. So we have here a 10 volts or V sub M of 10 volts. And then as you can see right here, it will pass as one diode only. Okay. So before we have 4 diodes, but right now we have 3 resistors and then 2 diodes. So if you're going to take a look on this one, if we have a positive half cycle, it will pass us on the right side. So it will not pass through here since this one will become reverse bias. Okay. And then as our positive voltage is passing through here, okay, it will divide it into 2 parts. So it's either on this one or this one. So as you can see, our voltage output now will be divided by 2. Okay. And then as it passes through here and then through here and then going back through our negative. So the same concept with the negative. Okay. So if it's negative, and then it will pass through on the left side. So negative to negative and then positive to positive. So what is passes through here, our V sub O or our voltage input rather will be divided into 2. So it could be right here or going through here. Okay. So either of those two, it will be divided into 2. Okay. And then they will gather here and then go back to our negative. So to make it simple, we have these. All right, so this is just a solution for the positive. For the positive, it will pass through here, and then so we will be divided by 2 and then go back to our ground. And then if you're going to redraw the circuit, so you will get this kind of circuit. Okay, so as our V sub I passes through here, so it will be divided into 2. All right, so if we have a 10 volts of V sub M or V sub I, then just divide it by 2. So 5 volts here, and then another 5 volts here. So thus, here V sub O is equal to 1/2 V sub I, or 1/2 V sub I, or the maximum, or V sub I max. Okay. So if you're going to get the value of those V sub I, so 1/2 divided by 10 volts. Right? So just divide our 10 volts. So we will get now a 5 volts as our V sub O. Okay, since of course our V sub I will be divided into this part. Right, so 5 volts here and then another 5 volts on the other side. And then here's the solution for the negative half cycle. So for the negative half cycle, the conduction rule of the diodes can be interchanged. Okay, so the same process. So it's just either passing through here or here and then divided by 2. Okay, so that's the idea about it. So we have a positive and then a negative 5 volts. So for the negative half cycle, the conduction rule of diodes can be interchanged. You've already read that one. So the absence of 2 diodes in the bridge results in the reduction in the DC output with a magnitude of VDC is equal to 0.636 times 5 volts. So of course, you will get 3.18 if you're going to solve this one. So in here, as you can see, this one is a full bridge rectifier or full wave rectifier, since this one is accepting a positive half cycle and then a negative half cycle. But with the loss of 2 diodes, okay, is the same with dividing our voltage input into 2. Okay, so if you want to get the full potential of your full wave rectifier, so you should have another 2 diodes here. All right, so yeah. Okay, so that's it for VDC. So of course, right after this full wave rectifier, you're going to have a quiz. Okay. So given is 20 volts, and then all of the diodes are silicon, and then solve for V sub O and VDC. So we only have one number for this one, full wave rectifier. So I think 5 points for the V sub O and then 5 points for the VTC. Okay. All right. So moving on, we have here the centered tap full wave rectifier. But before that, so do you guys have a question or clarification so far? Are you guys still there? You guys still listening? All right. So from Miss Elaika, none. From Mr. Pulmano, none. What about the others? Question or
None,
clarification?
sir.
None, sir.
All right. So if you guys say so. So again, feel free to interrupt me anytime if you have a question or clarification. All right. So moving on, we have the second type of the full wave rectifier, which is a center tap full wave rectifier. Okay. So the wire is adjusted in such a way that it falls in the exact middle point of the secondary winding. So we have here the center tap. Okay. 1, 2. Okay. And then we have the center type line here. So this one is a center tap transformer, 1, 2, and then the middle side is a center tap. So the center tap transformer works almost similar to a normal transformer, okay? So like a normal transformer, the center tap transformer also increases or reduces the AC voltage. So however, a center tap transformer has another important feature. That is the secondary winding of the center tap transformer divides the input AC current or AC signal BP into two parts. Okay, so later on we'll discuss what are those two parts. But for now, as an overview for the center tap, so this is what we actually use for the step up or step down transformer. Okay, so it is with the idea of the center tap. So depending on the windings or the winding ratio, so some are or mostly are 1:2. Okay, so that is a step up rectifier. So let's say we have 10 volts here. Since we have a ratio of 1:2, then on the second windings, it will now get 20 volts. Okay, so 10 times 2. And vice versa, we have step down rectifier, so 2:1. So if we have 10 volts here, will be then on the second windings, we'll get 5 volts uh, as a voltage input or voltage source on the second one. All right. So moving on, we have here the upper part and then the negative or the lower part rather. So the upper part is the positive voltage V1, and then the lower part, which is the V sub 2, is a negative voltage. So when we combine these two voltages at output load, we get a complete AC signal. Okay, so we have a positive half cycle and then a negative half cycle. So in a half wave rectifier, you cannot process a positive and negative at the same time. Okay, so it will only accept one polarity, but in here it will accept two polarities at the same time. So positive on the upper side and then negative on the lower part. So V total is of course V sub 1 plus V sub 2. Okay, so this is the common one. Okay, always like that. So whatever is our V peak will be divided into two. So V sub 1 and then V sub 2. So the voltages V sub 1 and V sub 2 are equal in magnitude but opposite in direction. Okay, so that is the voltages V sub 1 and V sub 2 produced by the upper part and lower part of the secondary winding. So again, I'll just mention this one. This is our primary winding, the left side, and then the second one is the secondary winding. Okay, are 180 degrees out of phase with each other. So however, by using a full wave rectifier with a center tap transformer, we can produce the voltages that are in phase with each other. Okay. In simple words, by using a full wave rectifier with center tap transformer, we can produce a current that flows only in single direction. Right? So again, what is center tap full wave rectifier? So a center tap full wave rectifier is a type of rectifier which uses a center tap transformer and two diodes. Okay, so we have a center tap transformer and then two diodes, and then of course our load resistor to convert the complete AC signal into DC signal. Okay, so this one is still a full wave rectifier. The center tap full wave rectifier is made up of an AC source, okay, a center tap transformer, two diodes, and a load resistor. Okay, so the AC source is connected to the primary. Okay, this one is our AC source, and then the second one, a center tap additional wire connected at the exact middle of the secondary winding, divides the input voltage into two parts. So as you can see right here, we have a center tap transformer, and then the second one is the secondary winding. So this this center tap transformer, this one on the middle, is the one that is dividing our AC source into two parts. Okay, so as it passes through our second windings, it is now divided into two, the positive and then the negative. So the upper part, oops, let's try here, yeah. Right, so the upper part of the secondary winding is connected to the D1, and then the lower part of the secondary winding is connected to the D2. So this is very important. As always, we have this fixed setup. Okay, so this won't change. So we have here D sub 1 and then D sub 2 on the lower part. So as always, we have a diode here and then another diode here. And then the middle one is a load resistor. So if there's one that is missing, we cannot call that, or we cannot say that this one is a center tap full wave rectifier anymore. Okay, so we have a fixed setup of D sub 1 here and then D sub 2 on the bottom and then R sub L on the middle. So in that way, we can have a full components of a center tap full wave rectifier. Right, so moving on. So both diode D1 and D2 are connected to a common load RL with the help of center tap transformers. So the center tap is generally considered as the ground point of the zero voltage reference point. So our RL is considered as the ground point. So positive to ground and then negative to ground. So here how the center tap full wave rectifier works. So let me just make it real quick. So this one is as a complete info. So again, we have here the AC source on the primary windings. And then we have here the center tap transformer, as I mentioned a while ago. And then this center tap transformer is the one that is in charge in dividing our AC input into two parts. So it is already dividing it in the positive part and then the negative part. Okay. So during the positive half cycle of the input AC signal, terminal A, so this is very important, so take note on this one. Terminal A become positive, okay, take note. Terminal A become positive and then terminal B becomes negative. And center tap is grounded 0. Okay, so the positive terminal A is connected to the P side and then the terminal negative B is connected to the D sub 2. Okay, or on the other side. So the diode D1 is forward biased during the positive half cycle. Why? Because if you're going to take a look on this one, we have here the positive and then a negative. So on the D1, positive to positive, negative to negative. So this one will become a forward bias. But on the other side, negative is connected to the positive. So this one will become a reverse bias or an open circuit. Okay, so that's it for the positive half cycle. And then, where is that one? During the positive half cycle, this one. And then during the negative half cycle, okay, take note, okay, our signs of the terminal A and then terminal B will now interchange. So this terminal A will become negative and then terminal B will become positive. So that's how our center tap full wave rectifier works. So for the positive half cycle, we have positive minus, and then for the negative half cycle, we have negative and then plus. Right? So as you can see, if we have this kind of setup, negative now is connected to the positive, so that will make this diode a reverse bias. And then this side is positive, positive, or positive terminal now is connected to the positive side of the D sub 2. Thus, this will make it a forward bias. Okay, so the flow of electrons or the flow of electricity will now pass through here. Okay, and then the other one is just completely an open circuit. All right. So for positive, it will conduct here. For negative, it will conduct on the lower part. So thus, the diode D1 allows electric current during the positive, and then the diode D2 allows the electric current during the negative half cycle of the input AC signal. Okay, so if you're going to take a look on this one, we have the full AC input, and then the D1 current will only accept positive half cycle or positive current or electric current. And then for the D2 current, the other one will accept, of course, a negative current. Okay, this one, and then this one. And then if you're going to combine those two, of course, we'll now have this complete full wave rectifier or rectification process, right? So complete cycle. So thus, a small voltage is wasted at the diode D1 and D2 to make them conduct. However, this voltage is very small as compared to the voltage appeared at the output. So this voltage is neglected. So the diodes D1 and D2 are commonly connected to the load RL, and then so the load current is the sum of the individual diode currents. So we know that a diode allows electric current in only one direction. So from the above diagram, we can see that both the diodes D1 and D2 are allowing current in the same direction. So we know that the current that flows in only single direction is called the direct current. So the resultant current at the output load is a direct current or a DC. However, the direct current appeared at the output is not a pure direct current, but a pulsating direct current. So if you're going to take a look at this one, yes, they are in a DC current, but it's in pulsating point. Okay, so it's like that, pulsating. Right, so the value of the pulsating direct current changes with respect to time. So this is due to the ripples in the output signals. So the advanced part of this one is with the use of filters. So if you're going to use a capacitor and an inductor, then it will reduce the ripple. Thus, this pulsating direct current will become more smooth. Okay, and then the average output DC voltage across the load resistor is double that of the single half-wave rectifier circuit. Okay, so we have here an example. Do we still have the time? Still have 1 minute. Anyway, I think we can finish this one in 1 minute. If not, then we just have to continue this one on the part 3. So as you can see right here, we have a V sub 1 of 10, and then we have a ratio of 1:2. And then we have the V sub 2 and then V sub 2. So it's divided into 2 parts. So for you to be able to get those V sub 2, so you should get the ratio. So V sub 2 is equal to N2 divided by N1 times V sub 1. So twice of our V sub 1, okay, which is now our the result of the V sub 2, since it's 1:2. So 10 here will become double, will become 20 volts. And then for the PIV, so just get the twice of the VM, okay, and then in our VM, so you have to consider the voltage threshold. All right, so I think we don't have enough time anymore, so goodbye for now, and then we'll see you on the part 3. So I think we'll just